that's not good. And the problem with lists is you can have duplicates and things are ordered, and there's no easy way to determine where any individual name would actually be in that list without going through and looking. So you have to search through the entire list to find something. Sets, like I said, are unordered, but they also contain no duplicates. And aside from that, they also allow us to use set operations, right? So if we start off with this set, right, this creates an empty set. Let me find my notes so that I can leave this page and still remember what exactly it is I'm supposed to tell you. So before we make this thing faster, let's kind of go in here and play with sets a little bit. You know what? I will play with sets down here. Okay, so we can have S equals set, right? The set call creates an empty set. Empty set looks like that. We can start adding things into it. So we can say, or actually we can create a non-empty set. You can initialize a set from a list by providing arguments to the set. So if we do set range, what does this say? 0, 11, 2, 0, 11, 2, right? Our range call should generate a sequence of numbers from 0 up through 10 by 2. So we can look at S2, and S2 now has 0, 2, 4, 6, 8, 10. Notice they're in order. That's luck. Actually, it has to do with the hashing algorithm, but for now, we're going to just say that that's luck. We can come in, and I'm going to grab this one because it's starting to get longer. We can do something like this, right? We can set up V to be a list. And notice that in this list, we have two 32s. I think just two 32s. And now we can say S3 equals set of V, right? Give it a list. S3, length of V is 9. Length of S3 is 7. Two 4s and two 32s, right? So S3 has all the entries from V, but it only has some.
I can't see your code.
Huh. Why is that not coming through on the code? All right. For some reason, it's not switching when it's supposed to switch. Thank you. Okay. So for S3, right, we can say the length of V is 9. The length of S3 is 7. S3 has all of the entries that occur in V, but it doesn't have any duplicates. So 4 only appears once, and 32 only appears once. Everything else appears. We have a mixture of strings and a mixture of integers. Apparently we don't like floats, but we could throw some floats in there if we wanted to as well. Okay. We can also add things in. Like we can say s.add 5.7 just to get a float in there. We can do s.clear. That'll take the float out of there. It'll take everything out of there. So these allow us to add and get rid of things in a list. There's the idea of set difference. Set difference. Let's see. If we look at S1, wow. S2, right? S1 has that was supposed to be S1. If we look at the difference between S and S2, S1 is empty. S2 has 0, 2, 4, 6, 8, 10. So that just takes out anything that's in S2 from S1, but I don't know why I would have that there since there's nothing in S1. Let's say instead, let's do S3. Dot difference S2. Right? So now we look at S3. S3 has hello, 32, 64, 256, 4, spam 8. And S2 has 0, 2, 4, 6, 8, and 10. So what we've done is we've taken out the 4 and the 8 from S3, and that leaves hello, 256, 32, 64, spam, which is 5 things. There's a notation for this. S3 minus S2 gives us the same value. The minus sign is the difference operator on sets. We can do intersections. So if we want to do S3 intersected with S2, this should be the two values we took out, 4 and 8. We can also do S3 dot right? We can do union. And I'm going to start using the short notations. You can look these up. Unions, all those operators have word operators as well. That gives everything that is in S3 plus everything that's in S1 or S2. We can look for subsets. Right, that's a subset or the same set. This is just a subset. Both of those are false. Let's say right, we have S1, 0, 2, 4. We have S2, 0, 2, 4, 6, 8, 10. S1 is a subset of S2. Oops. Sorry about that. This should be set list range. Right? It's also S2 is a proper subset of it, or is a less than or equal to of S2. It's not less than S2, right? The less than sign says it's a proper subset. It's completely contained within. And of course, we have the superset as well. S2 contains S1. S2 is greater than. Come on. Right? S2 is greater than or equal to S2, but it's not greater than S2. All right, so all of these are operations on sets. And these are Boolean operators, right? They return true if the operator, if S1 is a subset of S2 or S2 is a superset of S1, it returns true. Otherwise, it returns false. All of the comparator operators, the subset operators, that's the way they work. And make sure that you look up, the full names of these operators as well. There's a little cheat sheet, or they're all listed. They're all listed on the sheet if you spell them correctly. And we've gone through a bunch of these. If we want to look at this briefly, you guys should know Venn diagrams. We're a little bit behind because of all the questions about the test, so I'm not going to go into this a lot, but we can kind of take a look at this from the standpoint of a Venn diagram. Come on. Right, so if we have our Venn diagram and we have two entries, right? Let's say this is comedies, tragedies, right? Sometimes there's dramatic comedies that would fall into this area. This whole area is comedies. This whole area is tragedies. These are tragedies that aren't comedies. These are comedies that aren't tragedies. These are both, right? So the union operator is everything. Both of those. The intersection operator is this section. C minus T, the difference operator, is this section. What other operators do we have here? There's this symmetric difference that I didn't show you. The symmetric difference is all of these plus all of these. And let me show you that in just a second. I knew there was one more that I was missing. Okay, it doesn't include this stuff in the middle, the stuff that's common to both. So if we look at S2 and S3, remember that 4 and 8 are common to both. So if we come through here and look at, and that doesn't change for some reason. It was changing before. Okay, so if we remember, S2 are the even integers to 10. S3 has 4 and 8 in it. S2, symmetric difference, S3 has the union of the two sets except for 4 and 8, which are common to the two of them. So that's essentially the union the union minus the intersection. Nope. Oh, I'm sorry. There we go. The union minus the intersection. And you notice that these sets are equivalent, but they're in a different order. So that's one of the things you have to be careful of, is unless we impose order by essentially converting them to lists, we don't have order, and we have to be very careful of what's actually going on. All right, so I'm going to skip, let's see, let's go back to our spider for now. Is that stopped running? Yes, it took 796 seconds. So this essentially gets slow very fast. That's what we call an order of n squared operation. And we'll get into that more as we kind of continue down this path and start talking about sorting. Yeah. So they found 120,000 different people in 796 seconds. That's, over 10 minutes, 13 minutes roughly? A little bit more. So 13 and a quarter, let's say. So we get slow very fast. Between the second solution and this solution, this has 10 times the number of people in it, but it turns out that it runs 50 times more slowly. 17 seconds. $7.96. Well, more than that. Yeah, 46 times more slowly. 40. Did I get those right? 17. Yeah. Okay. So roughly 46 times more slowly, despite having only 10 times the number of entries. So that means that, you know, if we double it again, it's going to get even more slow, or if we multiply it by 10 again. So we need a better solution. So let's look at a solution using sets. All right. Well, to do the set, I mean, basically we have to just do this, right? We'll start off by changing our name set to name set. And we can do this. If name not in name set, we could do name set dot add. Right, this is just a straightforward replacement of sets, of lists with sets. Right now, the only thing we've done is we're still asking the same question: is name in set? And adding the set in if it is. And I'm not even going to bother doing the quick ones. I'm just going to go straight to IMDb data and name list is not available. So we probably should make this name set. Is there any more places? Let's see. Line 36, line 36. Okay.
Wait, line 40, doesn't it have name list?
Does it? Ah, you're right. Thank you. You've saved us from yet another crash. I thought there was another one, but I didn't see it right away. That's not slowing down at all, is it? 2 seconds. And I can tell you that at that point, the print statements are probably starting to predominate. So the question is, what's different? And the answer is this line. For sets have to be, elements in sets have to be something called hashable. In a list, you don't know where you've put things. With a set, you put it wherever its hash tells it to go. So you always know where to look. So instead of this taking the length of name set to determine, right, for a list, you have to go through the entire list and see. For a set, you don't have to go through the entire list and see. You can ask this question, you figure out where it would be if it were in set, and then as soon as you've made that determination, it's a single, instead of taking the length of the list, it's a single operation, or a constant time for every element. And it's a little bit more than that, because we can actually take this out. Sets have to maintain a uniqueness property. We don't even have to ask if it's in there. We can just add it. If it's a duplicate, it won't get added. They'll try to put it in the same spot. They'll see it's already there, and they'll say it's already there. It's no error at all. So we can go in and do this the same way. I don't think this will actually give us much of an improvement, if anything. Right? So it's much simpler to ask this question. This is a much faster operation when you're using sets, right? You don't even have to ask if it's in there. You can just add it. But if you do ask, even that ask is a lot faster. But we can break it. I'm still going to leave this way, but let's just do a little loop on this. Let's say for n in name set, if n equals name, print, found it. So this is essentially what we're doing. We should be setting some flags or something instead of just printing out found it. But when you walk through a set, if you do it this way, right? If you use an explicit for loop and look at each value, you're essentially serializing the data. And now you're going to see that we start slowing down, and we're no better than the list solution. And again, the reason is because as we go through here now as the name set gets larger, we have to walk through every element because it's being imposed on us by this line 33. We're no longer able to take advantage of the fact that finding something in a list is incredible, or in a set is incredibly fast, right? We're already way over 2 seconds. And it's not just the prints of found it. Okay. So don't do this. You don't have to test before you put something in a set at all. But if you do test like this. Right? You don't need to do this. Some of you will feel the need to do it anyway. If you do it this way. That won't cost you anything, or won't cost you very much. Oh, what did I do here? Forgot the knot. Okay, so 3.2 seconds this time. All right, so just keep that in mind as we go through. You will all make the mistake of serializing a set at some point. We'll try to catch it on submittee early, but you're all going to do it because we all have done it. We talked about a lot of this. I think the other thing we want to talk about is the list is ordered, but it's not. This says neither the set nor the list is ordered. The list has a specific order based on the indices of the names, but it's not coming in a sorted order. So we can do a sort on that, or we can do a sort on the set. And if we want to sort the set, we have to convert it to a list. So we want to make sure, we want to be kind of sure that we're done with our set operations before we do the sort. Because the set, we can't put a sorted list back into the set and expect the sorting order to be preserved. Sets have no specific order. Okay. We'll talk a lot about hashable and hashing because this test in a set takes constant time. It can be done in essentially a small subset, a small set of operations that doesn't grow with the size of the problem. That means that we only have to, when we go through this, the entire time spent processing, right, every time through this loop costs the same. So this becomes an order of n algorithm. If we allow this to grow, and if we allow it to grow such that this test for a list becomes on the same order, right? If we have 10,000, it's kind of 10,000. If we have 200,000, the list grows to kind of 200,000 elements. Then each loop through this list takes time n, and there's n lines in the file, so that's an order of n squared operation. So we'll talk about this a bit more a little bit later on as we get into this and dictionaries and everything, as we get into sets more and dictionaries and such. But that's the stuff to keep in mind. That's the material we have for you. We'll do a review on Thursday during this period. I will answer your questions, show up. I will post it as soon as I can afterwards. But it's going to be 4 o'clock, and whether you'll have a chance to view the end of the lecture is a little bit questionable. Anyway, that's it.